Good morning, students. As we have already discussed about mutual inductance and the various factors on which the mutual inductance depends, now we are going to do the last topic of this chapter, that is the mutual inductance of two long coaxial solenoids. So I have drawn two coaxial solenoids. One is S2, which is green in color, and the other one is S1, which is shown as red in color. So there are two long coaxial solenoids. They both have the length L, and N1 are the number of turns per unit length of the inner solenoid, that is S1, and N2 are the number of turns per unit length for the outer solenoid S2, which is of radius R2. Now imagine that the current I2 is passing through the solenoid S2, which sets up a time varying magnetic flux phi1 through S1. That is, when the current I2, the time varying current, that means it is a variable current, when it is passing through S2, it produces the magnetic flux phi1 in S1, and as a result the S1 will further show the mutual inductance, right? So phi1, that is the time varying magnetic flux phi1, which is through the S1, is actually directly proportional to the current I2, because as we have already discussed, the current in one solenoid will result in the induction in the second coil, right? So the first coil, here I have taken S2, so I2 current will result into the flux in the first solenoid S1. So phi1 will be written as M12 I2, where M12 is the coefficient of mutual induction of solenoid S1 with respect to S2. Now write this equation as number 1. The magnetic field due to current I2 in S2 will be given as mu naught N2 I2, right? And the magnetic flux through S1 will be given by this magnetic field and the area and the number of turns of its own. Because the flux coming in S1 is because of the magnetic field in S2. So the magnetic field will be considering of S2, but the area and the number of turns will be considered for S1, because flux we are calculating for S1. So the flux will be the amount of magnetic field crossing the area of S1. Okay. So N1 is the total number of turns. So it can be written as the number density multiplied by length, as I have told you that N1 is the number density of S1. So write the value of B2, put the value of B2 from here in this equation. Area can be written as pi R1 square, and number of turns are N1 into L. So when you just multiply it, you write it, the equation number 2 will be obtained. Now this phi1 we have found out by the traditional definition of flux, that will be the magnetic field, area and the number of turns. Okay, and this is the flux which we have already obtained, which is by the definition of the mutual inductance. So comparing equation number 1 and equation number 2, you get the value of the mutual induction of S1 with respect to S2. Now similarly we can find out the mutual induction in solenoid 2 with respect to 1. So in that case we need to find out flux 2, that means the flux in the second solenoid. So as per the definition on the mutual induction, I'll say that flux in 2 will be mutual induction in solenoid 2 with respect to 1, and the current when it is being passed through S1. So now the current is passing through S1 and it is resulting into the mutual induction in S2. So we are doing the reverse case now. Right, so where M21 will be the coefficient of mutual induction of solenoid S2 with respect to S1. Right, now again another definition, which is the traditional one, in which we can say that phi2 is equals to B1, because the magnetic field is to be taken of the other solenoid, area and the number of turns. Now in this case I will be taking the area A1 only. Ideally I should have taken B1, A2, N2. This should be the value of phi2, but I am not taking A2. The reason for this is that the solenoid S1 is smaller in area. The radius is smaller. and we know that there is no magnetic field outside the solenoid. So whatever magnetic field lines are, they are present in the smaller area only, which is the inner solenoid. Okay, so the magnetic flux due to S1 is confined only inside S1, right? Because we are assuming it to be an ideal solenoid, very long in length. So there is no magnetic field outside S1. So if the magnetic field is not present outside S1, then we cannot consider the whole area in which the magnetic field lines are passing through. Okay, so if the magnetic field lines are passing through S1 only, then the area in which the magnetic flux can be calculated is also going to be the area A1 only. Okay, because the inner area is having the magnetic field, outer area is not having magnetic field. So if this area is not having magnetic field, so the flux cannot be counted here. So the flux is ultimately going to be counted in this much area only. So that is why I have taken area A1. So just put the values of B1, A1 and N2. Now proceeding in the same manner, I have just put the values of B1 as mu naught N1 I1, A1 will be pi R1 square and N2 will be N2L, right? And when you will be just putting these values and comparing equation number 3 and equation number 4, then you get that M21 is equals to mu naught N1 N2 pi R1 square L, which is same as that we have obtained for M12. So we found that M12 is equals to M21. Right? So thus the coefficient of mutual induction of two coils, on what factors it depends? It depends upon the geometry, their separation and relative orientation. Relative orientation we have already discussed when we were doing the coefficient of coupling. So as you can see that it depends upon the radius and the length. So it depends upon the geometry and their separation. So this is how we can find out the mutual inductance of two long coaxial solenoids. Hope you have understood.